This past spring semester, I participated in the AY-REU program here at the University of Cincinnati. It stands for Research Experiences for Undergraduates, and it's a very great program to get young people like myself engaged in research at the university. I worked on a project with Dr. Kelly Cohen on developing a 3D printed Octorotor platform. Now, what was the whole point of this? Well, it's to design and manufacture a small 3D printed octocopter for stable indoor flight. Well, first of all, what is an octocopter? It's a multi-rotor UAV platform with 8 rotors. It's obviously battery powered, and it has redundancy in the fact that it has 8 rotors rather than 3, 4, or 6, which gives it increased reliability with certain algorithms that we're going to write in the future to have it capable of recovering from a motor failure. And this is very important when it comes to safety and certification for when they're implemented in the national airspace eventually. It has a global impact on a variety of industries. You may have seen Amazon's delivery drones or firefighting drones, is what UC's Sierra project focuses on specifically, and it could also impact search and rescue all the way to agriculture. Here's some of the nomenclature that I'll be using throughout this presentation. If you're not familiar with the radio control hobby or UAV hardware. So review this, and you can pause here and continue on with the rest of the presentation. My project objectives were to design this octocopter in Solid Edge and print all the materials with a MakerBot 3D printer. I'm then going to assemble the octocopter, and I'm using the APM 2.5 flight controller from 3D Robotics, which I will then tune the gains for the stable flight characteristics that I'm desiring. The whole point of this is to have it completely 3D printed, so that way we can replace our parts without having to go to a manufacturer and buy them, which that's why the most important emphasis was on the 3D printability. Obviously it needs to be stable, especially for indoors, because it's such a small profile. It should be able to fly down a hallway pretty easily. We're hoping for greater than 10 minutes of flight time with the additional payload, and the modular arms are a must, so that way it all fits on the build tray. If you're not familiar with Horsefly is a project that our graduate student Weiwei has worked on in partnership with AMP Electric Vehicles out of Cincinnati. It's a certain style, which you'll see in a moment here, which we deemed Horsefly, and it has to do with how the arms are forked instead of the conventional 8-arm layout. So my work for this semester will include creating a thrust stand and recording all the motor data that comes out of those tests. I will also need to predict the weight for all the components, as well as weighing each individual hardware piece. I need to ensure that the MakerBot's going to print at the quality that I want. I need to solder all the electronics together, install the Octo frame firmware on our flight controller because there are tricopter and quadcopter options, but I need the Octo. Weighing it and testing it and tuning it will be the final test at the end of the semester, so hopefully that goes well. I want my airframe to exhibit modular characteristics as well as being durable in the event of a collision with the wall. Hopefully the props are the only things that break in this case. It needs to be easily printable, so that way all of the components are not too large for the build tray that we have on our MakerBot, which is why it's going to be built in 5 separate pieces. I am an RC pilot, and I have been for about 4 years now, so I have the pilot skills and hand-eye coordination, and I just have a natural feel for the aircraft for what it should be doing, so I know what is unstable and what is stable when it comes to the feel of the octocopter. And so I don't want any drift, I don't want sluggish control responses either, and there's such thing as having it too high of tuning, and then it gets into the shakes, the gyro shakes. I'm using the RCX ESCs and motors. They're extremely small motors, but they're surprisingly powerful. It's on a 3S battery, which is about 11.1 volts nominal, but it's about 12.6 max. And the props are 3-bladed 5-inch props. My initial thrust tests involved the motor mounted high above everything, no restrictions whatsoever. This was kind of an ideal situation, but in fact in the real application there's going to be an arm here, and so I've attached a simulated arm which is going to add some inefficiency to the propeller, give it reduced thrust, and we'll see that in a mathematical model. Alright, so after the data was collected for both restricted and unrestricted thrust tests, I've applied a trend line to the restricted thrust and gotten a mathematical model for that. You can see towards the upper right hand corner that the restricted thrust was actually affected by that arm put in place, and so this is important in considering how much maximum thrust I will have towards the upper limit of the spectrum. Interestingly, current and power both were not as affected by the restriction in the airflow. But you can see that compared the restricted and unrestricted thrust, the power consumption and current consumption were similar, but the thrust had a loss of about 12.7%. Alright, so let's get into the how I designed the airframe. So initially I wanted to make it the smallest profile possible with the 1-inch consideration between the props. Now you can see in black it would be the traditional octo layout with 8 arms, kind of like a bicycle spoke going into the central hub. But I took the horsefly style inspiration from Weiwei's creation. Now this has 4 connections to the center body, and each forks out into 2 motors at the end of each arm. I designed this with 3D printing in mind, so the surface on the bottom, which is actually the top of the arm, is completely flat, so that on the build tray, the MakerBot, it doesn't have to build as much support material to make a clean build, and there's less chipping away of support material, and it's just overall a greener process and an easier process to clean up. The hub is just a cross. I did not have time to go in and optimize the design for weight savings, but there is huge room for improvement, which is good news actually, because it flies so great already, and it has a pretty decent flight time that there's room for improvement, and that's always good news. The landing gear was just kind of an afterthought. I needed some way to elevate the platform off the ground, and so these are clip-on, which means that there's no screws or other hardware that need to be added to add weight, and these are very light. As you can see, they're hollowed out in the center, and so these just lift the platform up off the ground so that the battery can go underneath it, and some wires can be tucked underneath as well. I used a MakerBot Replicator 5th generation, which has that sized build tray volume. I used the PLA filament, and the extrusion temperature we chose, just the default, was 215 degrees Celsius. So we didn't have exactly the best of luck with the MakerBot initially. This was the print quality. It was pretty terrible. So after replacing the print head, the quality improved greatly. There was no drastic warping of the part. The surfaces were nearly perfect. I chose a 25% infill for the arm, which is actually still too strong. I tried printing 45 earlier, and there's much room for weight savings. I used the APM 2.5 flight controller from 3D Robotics. I've had experience with this in the past, and they work very well. It's an Arduino derivative with all of the hardware like gyros and accelerometers on the board itself, and they have a user interface that's pretty easy to use and set up to calibrate everything, and to get all of your parameters set up. And it has 8 PWM outputs for each individual ESC, and this is one of the few boards that is capable of handling a Octocopter platform. Once you get out of the ground effect, it's a lot better. The maiden flight we flew with the stock PID values that come on the board, and it did take off. It flew okay, but they needed toned down a little because it was a little shaky. So we turned down the P for the pitch and roll on the stabilize, because there are two different PID loops. There's a stabilize and a rate. And so those were decreased just slightly because it is a smaller platform, so it'll be slightly oversensitive if overtuned. The most interesting result, I think, to come out of all of the testing was to find the optimum battery weight for maximum flight time. So if you think about it, if you keep adding battery capacity, you're increasing your weight as well. So eventually you'll reach a maximum in the function where if you add too much battery weight to try and get the most flight time, you'll actually hurt yourself by adding too much weight, because the motors can only lift so much, and eventually you start weighing yourself down. And so with 1350 milliamps, that tiny little yellow battery, the flight time was only 5 minutes. It was super light, super nimble, but the flight time was only 5 minutes. Now if you roughly double that, you got about 4 extra minutes. Now if you go to 4400 milliamps, we got 14 minutes, which I was very surprised and happy about, because that exceeded our 10-minute expectation. And if you bump that up to a 5000, you can see the major difference in battery mass. It did not increase flight time at all. That's 600 extra milliamps, but that's 70 extra grams that hindered the flight time performance. And so somewhere in between that, or about 4400, is the maximum in that function for the maximum flight time. This platform, as I mentioned before, has tons of potential. There are a lot of areas that I could cut weight in the arms and the central hub. The whole reason I designed this with 8 rotors is so we can cut off one and see how our control algorithms deal with a lost motor, to have 7 or 6, however many we can operate this aircraft safely to the ground in the event of a motor failure. I'd like to thank the NSF for providing me with the grant to complete this research, also for the AY-REU program at UC, as well as my amazing professor, Dr. Kelly Cohen, who supports me in everything I do. He provides me with funding and a great lab to work in. And my graduate assistant advisor, Mr. Brian Brown, is always a great help when it comes to lab stuff. With that, I thank you for watching, and I hope you enjoyed. Thank you.